Hello. This is our second session about Caesar and Vigenere cipher encryption. And we're going to continue from the point where we stopped last time. And similar to what we've done before, I'm going to record the session independently from YouTube. And this will help us to have at least two sources of recording. One will be over YouTube. This is probably the most convenient to watch. And another one will be shared through our streaming server. It will have a bit better quality, but you probably will need a bit more compatibility. We'll face several compatibility issues. Anyway, last time we stopped at the moment of looking how clean function works in our script. And let me just recover this step, the state where we've been last time. So I'm currently logged in to the Octave server, and from the console I'm going to start Octave. And my first step would be to load the Caesar script and make sure that the two parameters, the two data objects are there. First of all, first one is our alphabet that it contains 26 characters. And the second one is a 1 gram table that contains 26 numbers or floating point numbers. So both of them are defined in my script, in Octave script over here. And last time we talked about clean function. So the clean function is used to actually clean up any text from characters that are not contained in the alphabet. And at the same time, it will uppercase, lowercase characters. So let us see how it works. We have to use clean as and alpha. Result is hello world without a space, without exclamation marks at the end. Now let us talk about encryption. Let us just say that our key, encryption key, is 3. And now we need to do something to actually convert each and every character of the hello world text, the cleaned up version of the hello world. By the way, I would like to save it into another variable called S1. Now variable S1 stores hello world text written in all capitals. And my encryption key of 3 is stored in a variable K. So forget for a moment what you see here, and let us just think of how encryption procedure can be implemented. Encryption procedure is straightforward. It's not as bad as the breaking procedure, but both of them are actually relatively easy compared with what you want to do with the Vigenere cipher. So encryption, we have to take each and every character, and for each and every character we have to identify the character that it will be substituted with. That character to be substituted with can be identified by looking at the alphabet and shifting the given character certain number of positions to the right. We assume that the key is positive, so we always advance the position of the character and towards the end of the alphabet. So we know from the PDF slides that hello world will become course rock, right? And with the key of 3. So let us see how it works. We need to iterate through the through all characters of the given text, And let us do it by means of organizing a for loop. So I would say C equals to S1. In Octave, loops are different than what you have learned from other programming languages. Actually, there are a different number of loops existing in Octave, but the one that we're currently going to use, it's very much similar to for each loop in some programming languages. So basically, we create a character class variable C, and we want to assign each members of the string S1 on multiple iterations of that loop. We know that S1 not only it is a string, but it is also an array of characters. So we will be iterating through the array of characters, and on each iteration of that loop, variable C will hold the value from the given string, certain character from that given string. Now, what should we do on every iteration of the loop? We need to add number 3. That's at least what we know from the procedure, right? I probably don't have that slide here any longer, but the idea is to replace H with K. So we cannot simply add number 3 to character H because it's hard to say what will it be. But let us see how it actually. Let us just try to do this. So you know that in Octave, if you just execute a command composed from the name of the variable, its value will be displayed. So I assume that when I execute command C, the character that is currently pointed at the given loop iteration will be displayed. And let me also display the character that will be pointed by C plus K. And at the end, I will execute command end. So that is the end of the loop notation. What we have now is C is a character, and we can clearly see our entire phrase hello world. But when we add C plus K, we actually now dealing with implicit conversion of a character into integer based on the notation of ASCII table. And 75, it's nothing more but ASCII code of the character that is shifted 3 positions to the right from character H. To see this clearly, we probably want to execute ASCII command and see that, for example, character H had ASCII code of 72, H shifted 3 positions towards the end of the alphabet has the ASCII code of 75. So that conversion actually makes sense. Now, since we're not going to deal with numbers, we're going to deal with letters. We probably need to at some point convert characters to numbers and then numbers to characters at the end. We have pretty much a number of different tools to use this conversion, but let us see what exactly we can do. So, for example, if we are given with character A, we can convert it to the numerical value by means of using double function. Double actually returns not an integer value, but a floating point value with double precision. But in Octave, pretty much any entry is a double, and we can clearly see this here when we just introduce a variable I, an integer variable I, and execute command whose variable I will be identified as having double data type. So in other words, in Octave, every number is a double. That's good to know. So converting a character into double effectively allows us to identify the ASCII code of that character, which is 65 for A. Let us just confirm this. For character A, it is 65. So it is correct conversion. How about conversion in a different direction? We actually need to forget about presence of ASCII table at the moment and try to implement the entire encryption decryption procedure not with respect to ASCII table, but with respect to the alphabet that is given to us. And our alphabet is from A to Z. So, for example, if we want to convert character H from the character class to a number, we actually want to subtract the first entry of the array alpha, which is A. We know that subtraction and addition in sense of characters results in, first of all, conversion of a character into a number. So H gets converted to the ASCII code, and alpha of 1, which is A, gets converted to the ASCII code. And we can clearly see their difference of 7. Now, how can we deal with this 7? It's actually not that big deal, because number 7 now has to be added with the value of 3, which is K. That's if we want to encrypt it. And we now want to convert it. That is, I'm sorry, that's not the way. So number 7 becomes 10. And now we want to find which character number 10 corresponds in our array alpha. So now we want to use alpha of that value to identify the character. And now we can see that something wrong, because we know that hello world is going to be encoded with the key of 3, which is our K, into coarse row. So in other words, H with the key of 3 has to become K. The reason for us to receive J in this case is because we didn't account to the fact that alpha array is referenced from 1, not from 0. This is actually index in an array. So let us just hypothetically think that instead of H, we had A capital. We know that alpha of 1 is also A, so A minus A is 0. 0 plus 3 now gives us 3. But alpha of 3 is actually C. But from the perspective of the procedure, index of 3 is associated with the character D, because character A starts from 0. So in other words, instead of substituting 3 as index of alpha, we have to add additional 1 to get character of D. And in this case, our encryption scheme now will be just that. So H gets translated into K. That is correct. Now, what if the key is large enough and we get the value of this expression that exceeds 25? actually exceeds 26, this value may exceed 25. In this case, we need to apply modular arithmetics to calculate this value modulo 26. So in other words, we have to apply mod function over this and then 26. Right, so result is still k, and let me check if this result is correct by means of using, instead of k, I will use k plus 26. Result should be exactly the same, and it is the same, because 26 now, in this parenthesis, it appears to be an additional argument that is seen in the left-hand side of the modular arithmetics. Adding certain number that matches the right-hand side of the modular operation doesn't change the result. So in other words, 2 mod 12 is 2, and 2 plus 12 mod 12 is still 2. That's how modular arithmetic works. So when we added 26 here, it doesn't change the result, but it allows us actually to deal with large numbers. So let us now recover our for loop, and on every iteration, instead of displaying C, we will be displaying exactly this. Yeah, I probably had to substitute character H here by C. Now we've gotten our coarse rock. Okay. What issues this encryption, this implementation has? First of all, we hard-coded the value 26. That is never a good idea. So let me introduce value n, which will be length of our alphabet, and n is 26. So now I'm going to replace 26 by n. And that is our coarse rock. So instead of actually displaying something, we want to store that something and return it as a string at the end of the function. So in other words, we want to do something similar to is already done in our existing implementation. So now you probably have better chances to see this clearly, how the whole thing works. First of all, we create an empty array result. Result, just want to recap this. Result will be the variable that will be returned from the function. So any change to the result that will take place throughout the implementation of the function will be actually a returning value. We don't have explicit return statement, but we do have the result value. Now, implementation here, it's a bit different than what we use right now, because we convert characters into the ASCII, and then at the end we convert it back to the characters. So let me just say I don't want this whole thing. And on every iteration of the loop, I will replace it by this. What I've done in this iteration of the loop is something actually very simple. So let me say R at the beginning is an empty array. So if I will redefine R as R and then, for example, A, R will become an A. If I will redefine R as R followed by B, R will become AB. So in other words, it is one of the implementation, it is octave style implementation of a string concatenation operation. So R now will be collecting different components of the given text, of the encrypted text. That's what we do here. Result is first initialized as an empty array, and then on every iteration of the loop, we concatenate individual characters to the end of that array. So the only thing that we have to change here is to define n, which is length of alpha, and key is already given to us. Okay. Now at the end, we don't actually need to conversion back from characters. All right. So that is our new implementation of the encryption function, and let us test how it works. I'm going to save Caesar M script, and I'm going to push it to the Octave server, and I'm going to reload it on the Octave server. So now I can use C encryption, and I will feed S, which is unclean hello world, and then the second argument is supposed to be key, which is 3, and then alpha. Okay, that is definitely not what we want. And the problem from numeric to char. Okay, so it says that C encryption line 12, column 10 contains a problem. And it is implicit conversion from numeric to char, to character.
I don't think that's an error. I think it's just a warning telling you that it's happening.
Yeah, that's
it was doing it before.
Yes, thank you for saying this, but we're trying to develop a code that is free of any warnings. That's the goal, because a warning actually it's not a big deal, but this implementation can be made without warning at all. So the way how we can translate it, we probably need to introduce conversion of a character into a number here. And that would be now explicit conversion, which will likely be appreciated. And if we want to suppress that part of the output, we just need to put semicolon at the end of this statement. And now we probably good to try it again. So let me push it again to that tape server and reload it. Okay, at least we don't get this, but we still have implicit conversion. That's something that I might be missing. Okay, alpha of 1, that's another situation where a character gets converted to a number implicitly. So that issue I can't recall seeing in the previous releases of Octave. Maybe they tried to make it as explicit as possible to inform the developer about some implicit statements. But let us see if this will fix the issue. Okay. Too bad. That could also be a case that now we use alpha of, no, that's the correct one. And where is the character 10? I believe that was about character position 10. Any ideas? Something that I might be missing? Okay, alpha of 1, that's the character. So that is the number associated with the first entry of the alphabet. That is the number associated with the character that we want to encrypt. So number minus another number plus a number and everything a number. Okay, let us not to waste any more time here. Just make sure that I reload it and try it again. Okay, now I think I know what's the deal. They complaining about not character to numeric, but numeric to character. And
I think the array starts out as a numeric, and then it's getting converted to a character array.
which one you say?
The array result, I think it starts out as a numeric array, and then it's getting converted to a character array whenever you start adding things.
All right. Let us try it. It's very strange because if we already seen this on an example here with r equals to, oh, that's also a case here, but I don't remember seeing this error with the previous experiment. So what will be the workaround? Okay, that could be a workaround. When we first convert the array to character, array to string, actually, before doing any manipulation. Or we actually can think of using the strings instead of arrays. So if R is an empty string, and then we say R equals to str_cat of R and A, so we probably can stick with these two operations instead of arrays. When I say it is octave style, at least it used to be octave style in the past, actually MATLAB style from the past. Nowadays, it seems to be not the case any longer. So it is the result and the alpha array, the alpha character. Now we're going to concatenate to the result on every iteration of the loop, and eventually we will return that value. Okay, now we have the clear coarse rock. And let me save it into variable S2. And I want to raise the question, how can we decrypt the coarse rock back into hello world, assuming that we know the key? So you probably can guess that encryption operation is very much alike to the encryption operation, with the only difference that k needs to be a negative number. So if instead of s we would pass S2, which is encrypted version, and instead of 3 we would pass -3, we're going to get hello world back from coarse rock. And in this conversion, this part of adding extra n actually helps to avoid dealing with negative numbers, because result of adding of a negative number k, so k is now a negative number, may result in the whole thing to become negative, but adding of n will by design make it positive. So, and now calculation of the modular of the positive number, it's always an easy thing to do. So now we can state that the same function can be used for encryption and for the decryption. All right, let us talk about breaking procedure. The breaking procedure is pretty much implementation of that formula, but before we can implement it, we have to calculate statistics, because statistics is implicitly used via function f of c, but it is actually array of frequencies of particular characters. So there is a function already implemented here that is called frequency, but let me comment on its creation. The general idea of how we can calculate frequencies, we should calculate how many times every given character of the alphabet is seen in the ciphertext. So in our case, S2 is the ciphertext, and we want to count how many times character A is seen here, how many times character B is seen here, and so on and so forth, all the way to the character of Z. So we might need to iterate through the entire alphabet. That, by the way, is what we do in this implementation. And C equals to alpha is simply a loop that iterates through the alphabet. And on each iteration of that loop, we want to find whether or not a particular character of the alphabet is seen in the given string. And if it is seen there, if it is found there, we want to count how many times it is found there. So let us say we want to check whether or not character O is found in the given string. So we just want to compare all to the string. A character being compared to the string, that's very strange operation. Usually we compare string versus string, and from other programming languages, we know that comparing two strings would just return whether or not they're equal. But comparing a character against a string allows us to identify the fact that this character is found in the string. So all we need to do now is to count how many ones in that sequence can be identified, and that will be the number of times of character O seen in that character. So a find command actually returns array of indices, but we actually don't need array of indices. We just need to find the length of the array of indices. So this small statement helps us to identify how many times particular character is seen in a particular string. And then, since we actually have to deal with frequencies expressed in form of fractional number, by the way, adding up all these fractional numbers should always result in 1. Same we can say about adding up all numbers in the gram table. If you add them up, you should have 1. And an easy way to check this would be to consider gram table, or which is presented in form of an array, and apply summation operation over it. So it is almost 1. Some function given with an array simply adds up all the numbers. So the number 3 that we receive from executing this statement has to be normalized, because we shouldn't be just we should not just use the number of occurrences. We need to identify the frequency. And the frequency is that number scaled with respect to the length of the given text. So in other words, correct result would be this divided by length of S2, which is 10. Oh, that is the correct result. And if you look at the implementation of the frec function, this is exactly what we do. Again, that is the concatenation of the operation. Now we don't deal with characters. We are good because we deal with numbers now, and that is how we populate array of result. So for example, character A is not seen in horse rock. That value will be 0. And at the first position of the result array, there will be 0. So result array will contain same number of positions, same number of entries as number of entries in the alphabet, which is 26. So result will contain 26 entries. And once we will add them all up, concatenate them all up, we need to scale them all at once by means of dividing each and every character of the result array by the length of S. And this is sugar syntax of Octave. So we can multiply an array by a scalar. We can divide an array by a scalar. We can do many different things over an array. And that syntax divide equals simply means result equals to result divided by length of S. So we divide each and every entry of the result array by the length of S. And let me demonstrate how it works now. So I want to use, since I didn't modify the frequency function, I just want to use it over string S2. So we have 0 for A, B, C, D, E, F, G. So there is 0.1 for G, 0.1 for H, IJ 0.1 for K, L, M, N, O 0.3 for O, and so on and so forth. That's exactly the result that you can see on this slide. 0.1 for G, 0.1 for H, and so on and so forth. Now, as we calculated the frequency statistics for the given ciphertext, we want to implement this formula. And this formula is nothing more but a summation of products. And let me see what we already have here in the breaking procedure. In the breaking procedure, we are given with the text, with the alphabet, and with the gram table. Since the breaking procedure is supposed to return us a single value, that single value we want to be a key. By the way, let us see how the breaking procedure works. So we want to call it over S2, alpha, and gram. And it returns 6. So 6 is the expected result because is the most likely key for the coarse rock encryption. We know that it is incorrect result, but at least it confirms our thing. So in other words, the cbreak function does everything that is described in the few slides over there. Not only it implements the formula, but it also analyzes the entire array phi and finds the maximum value in this array phi. And not only finds the maximum value, but actually searches for the index of the maximum entry of the phi. So we initialize phi to an empty array because obviously it has to be populated with 26 entries. And we calculate frequencies of the given text. And G is initially set up for the gram. The reason for us to copy gram to local variable G from the parameter of the method is because on every iteration of that loop, the gram table will be modified. So for I equal to 0, it will be one version of this array. For I equal to 1, it will be shifted version of this array. So in other words, we have to deal with multiple versions of the array, and at the first iteration of that loop, the table, the 1 gram table, will match the given one because on the first iteration of the loop, we have no shift, or we have the key of 0, assuming key of 0. So the way it works, we just assume that gram, or the G that represents the gram table, is defined, and we implement this operation. As I said, we're talking about sum of products. Sum of products of F vector to the 1 gram table vector. In Octave implementation, we use some strange notation, sum of F period multiplied by J. And let me illustrate how it works. Let us say we have 2 arrays. A equals to 1, 2, 3, and B equals to 4, 2, 3. Okay. Now let us just assume for a moment that we want to implement similar thing. We want to implement summation of products. Summation of products of these 2 arrays. So if we just, so in other words, we want to implement 1 times 4 plus 2 times 2 plus 3 times 3. That is the result that we are looking at. From the linear algebra, you probably can recognize that this operation is very much alike to the scalar product of two vectors. And this is exactly what it is. We can actually implement this operation in Octave in a number of ways. For example, we can multiply A by transformed version of B. Transformed version of B is the column vector. And now we just multiply two matrices, a row matrix times the column matrix. If you apply the rules of matrix multiplication, you will get exact same expansion. An alternative form of doing the same and getting the same result of 17 would be to multiply A times B entry-wise. The problem with vectors in Octave is that multiplication operation is by default bound to matrix operation, but we cannot multiply matrix A by matrix B since they do have unmatched dimensions. If we want to multiply two matrices, their inner dimensions should match. So instead of doing this, we're using a period multiply, which is the notation requiring entry-wise operation. In other words, we apply entry-wise multiplication of A by B. And that's exactly what it is. 1 times 4, that is 4. 2 times 2, that is 4. And then 3 times 3, that is 9. And the only thing we need to do now is to add all values up to get the 17. Now in this case, this is just one of the implementation, summation of entry-wise product. And that is our value of phi for the given value of the key. By the way, how many different values of the key we are trying? We are trying 26 values of the key. That is slightly different form of the loop that you didn't probably see and cannot recognize, but the idea here is straightforward. We used to see loops like C equals to hello. On every iteration, character C gets a particular entry of the string hello. But recall the fact that string is an array. And another form of creating an array would be to write something like this. So instead of hello, 1 to 5, for example. Now on every iteration of the loop, our number will iterate from 1 to 5. So that is the case here. Length of alpha is the number, and length of alpha is 26. So we iterate from 0 to 25. And the way now it works, we calculated phi, and phi is a vector. It's a vector of 26 entries. And now we want to modify the table. The way how the table is modified is based on rotation. For the I equal to 0, this is that table. For I equal to 1, instead of, let me just scroll through. We have P of C minus I, okay? So P of C minus I for I equal to 1, instead of that number will be, okay, let me just sound it correctly. So for the character which is referred as C, we have to use the previous value. So in other words, for character G, we now want to use this number. For character F, we want to use this number. For character A, we want to use this number. And this effect can actually be achieved if we consider this table. Actually, it's not a table, it's a row. And we shift it one position towards the end. And what we see in our implementation, that is exactly the shift. Let me now show you how the shift works. So that is A. Okay. If we want to shift it one position towards the end, we probably want to write down A of end, which is the last entry of array A, and then A from 1 to end minus 1. Okay, so the very first entry gets moved from the last position, and then these entries that are referred A from 1 to end minus 1 occupy the rest of the positions. Alternatively, you probably would need to organize a loop and make a copy, but this is a single operation that we can utilize to actually implement the shift. And that's what we do here. So G, after the first iteration, will become shifted 1 gram table shifted 1 position towards the end. After 2 iterations, 2 positions shift, and so on and so forth. And then at the end of this loop, vector phi will contain all 26 values that are summarized in this table. And now we need to find the maximum, and not just find the maximum, we need to find the index of the maximum value. And the way we do this, we use the built-in function max. So max of phi is a single number. And then we compare single number against array. That operation returns a bunch of zeros and ones. And then we use the find operation to find all non-zero entries, to find index of all non-zero entries. Theoretically, it is possible that vector phi excuse me, will contain more than one non-zero value. But and this actually operation will fail because in this case result will be not just a single number but multiple numbers. But assuming that array phi is actually comprised from floating point numbers, and the probability that 2 numbers in this vector are identical is very low. So in this case, if it is a maximum, it will be just a single value. And that array of zeros and ones will contain a single one. All others will be zeros. So function find will find an index in that array, but that index will be referenced from 1. So that's why we subtract 1 to return the notation in the scissor sense. Okay? And we already know how it works because we already demonstrated it. Let me just do this again. What do we do with this 6? We can use the decryption procedure. Excuse me. We just use the encryption procedure over text S2, and we have to supply that key with the negative sign. And then at the end, we want to pass alpha and just execute to get our build lawyer. That's exactly the result of the first case. Now, let us see an example where this algorithm will actually work. The breaking algorithm will work. So let me probably find some longer text, and that seems to be a good candidate. Now let me say my S equals to this. Okay, I want to first encrypt it with the key of, say, 8. That is the encrypted version. By the way, if we encrypt it with the key of 0, we just see the cleaned version of the text. But we want to encrypt it with the key of 8. Now let's break it. And not only I will be just breaking, I will immediately try to decrypt it. As you can see, result is correct. And probably another way to see this would be just to show the result of breaking, which is 8. So the breaking algorithm allows us to identify the correct key if the length of the ciphertext is sufficiently long. So the rule of thumb here would be to have at least 20 characters in the ciphertext, and we will see how this rule can be applied to the more sophisticated Vigenere cipher breaking procedure. So again, at least 20 characters will likely, of the ciphertext, will likely give you a good breaking result. All right, so I'm going to repost the assignment for the CIS cipher. Some of you probably noticed that I forgot to close that assignment from the previous year. So what I'm going to do, I'm going to slightly modify this, and we'll post it for everybody's consideration. There will be an explicit announcement on this. So basically what I'm asking you to repeat that procedure, actually to implement that procedure over a given ciphertext and do it by hands, using your calculator, using Octave, using anything, but not using the composed script. So I want to see the way how you would attack the scissor breaking problem if you don't have that script and cannot just copy and paste entries from that script. So I want to see everybody's understanding of the scissor breaking procedure. And once you will be able to show the correct result, I want you to use now that script that I'm attaching to the submission and confirm that your breaking is correct. So manual and then automated breaking of some Caesar cipher. That's what everybody is expecting to do for the Caesar assignment. And our next tutorial in this series will be to demonstrate the use, the breaking of the Vigenere cipher, which is a more complicated version. Pretty much a Vigenere cipher, it is a bunch of Caesar cipher in one envelope. And to break the Vigenere cipher, we will need to apply multiple times. That actually shows us the only practically. That's much. Right. If not, then that's and I will announce the generic tutorial on the correlation to likely case tomorrow and the Okay. It's